I will shortly be pasting a link to the Google Forms. If you're interested in joining the research committee, please go to the Google Forms and sign up. Okay, so Ronnie manages a team of building performance specialists spanning all aspects of simulation and modeling, including daylight analysis, thermal comfort, and energy performance. He regularly collaborates with architects, engineers, and sustainability consultants to develop project-specific value propositions using dynamic glazing to create high-performance buildings where occupants can be fully productive and thrive. He strives to help designers and engineers with simulation-based guidance they can use to make informed design choices. He has degrees in architecture, facilities planning, and building simulation. A few table roles before we begin, before I hand it over to Ronnie. If you have questions during this webinar, please type them in the Q&A window. At the end of the presentation, I will read your Q&A question. Depending on if you have a follow-up, I can also unmute our audience for a discussion with Ronnie. Our presentation is expected to go for about 40 to 45 minutes. So we'll have the Q&A session at the end. Also, shout out to Alex, our new vice chair of the webinars working group, and who'll be joining us in that position for our first time today. With that said, I'll hand this over to Ronnie. All yours.
Okay, thank you, Gokul, and welcome. I guess good afternoon to all of you. Actually, maybe I don't know. Good night. Maybe you might be in different parts of the world. But that's the cool thing about IBPSA. It's really global kind of organization of simulation specialists. I thank you, Gokul, again for inviting me to give this talk. I appreciate the opportunity. You've already kind of given my introduction background. I will just add that I've kind of been with View Smart Glass, company's View Inc. The product is Smart Glass for about 8 years now, and my specialization, my focus is building energy performance, thermal comfort, and also measurement studies, actual sort of studies of thermal comfort. So today's presentation is going to be a mix of actual case study and some simulation studies that I've done. So hopefully there'll be some good discussion. I know it's kind of going to be more of a monologue for a while, but I'm definitely looking forward to your questions at the end, and then I'll share my email. I'm more than happy to continue with the conversation after this on one-on-one based on how you want to proceed. So with that, I'll get started, and as you can see the topic, we're going to talk about thermal resilience, specifically with electrochromic glazing. I really have just 3 main sections for today's presentation. I'm going to start with a kind of introduction that will give you some facts, getting everybody on the same sort of plane, so to say, around what is thermal resilience, some definitions. And also, probably many of you know what electrochromic glazing is, but I just want to kind of give a very brief introduction of the technology and how it works, so that way, those basic things will be addressed. And as I present, some of those things will make sense. And then I'll look at the measured case study, and then a simulated study, and then kind of we wrap up. Right. So with that, let's start with sort of just high-level basic definitions for thermal resilience that I'm sure most of you are familiar with. So it's really, a building's ability to maintain essentially habitable, safe indoor conditions under different forms of thermal stress, typically without active system energy inputs, which for the most part means without having HVAC. It's kind of an indicator of passive survivability. I think you might have heard this term, or passive habitability. So it's definitely something that's important, especially in environments where there might be vulnerable inhabitants, like long-term facilities or other kinds of assisted living facilities. So it is an important measure to check for when you're designing. Now, within thermal resilience, the emphasis tends to be more on the overheating, or avoiding overheating rather. than underheating, mainly because as you must have seen that there is kind of increasing frequency of heat waves, right, around the country and around the world. And then, of course, there is the constant urban heat island effect that's continues to multiply across all kind of built environments. So overheating tends to be sort of the bigger challenge when it comes to thermal resilience and passive survivability. Now, the thermal stress that leads to that is the trigger for thermal resilience in buildings can be because of weather events, which is fairly straightforward. It can be extremely hot or extremely cold, or it could be due to loss of mechanical systems or power failure, or it could be a combination of both. So in this study, I'm actually going to look at more a short-term kind of temporary loss of mechanical cooling on a hot day, as opposed to sort of the longer-term, like global warming-based resilience. That's of course an important part, a study too, but that's slightly different. This I'm looking more on a shorter time scale, more for a temporary situation where there is probably like an equipment failure or loss of some form of cooling when the outdoor conditions are relatively extreme. All right. Now, why is that relevant? So if you look at this image, most Class A commercial office, or I mean, most buildings, frankly, even multifamily buildings these days have a significant amount of glazing, right? Typically more than 50% glazing. And these tend to be like a low emissivity coating glazing, which has 0.25, 0.30 SHGC. So not very high, but still a decent amount of solar gain. And then the envelopes typically by code are getting pushed towards being more airtight, more insulated, right? As a result, I mean, what happens is it's a good insulator. It's good in reducing infiltration energy losses, but it can essentially trap heat inside the building, right? If there is no way to extract it out. And then typically these kind of curtain wall facades don't have much thermal mass, so they're not going to necessarily delay, the heat transfer from outside to inside. So that's another thing. And then finally, most of these buildings don't have operable windows, or if they do, there are very few. So all of these things combined definitely make it harder for a traditional sort of commercial office building to be thermally resilient, unless you really are thoughtful about the design. So within these different parameters, what I'm going to talk about is essentially, can electrochromic glazing improve thermal resilience, right, during a loss of mechanical, given all of these issues that, there's a few operable windows, airtight envelope, and all of those things. So now that we understand thermal resilience and why it's important, let's look at the technology. What is electrochromic glazing, right? So electrochromic glazing, and View Smart Glass is obviously the name of the product that we make, View makes. The technology is shown here. This is a cross-section of a pane of glass, and these are kind of obviously not to scale. These are a stack of metallic oxide layers, let's say, which are basically nanometer level thick. And what happens is when a low voltage is applied to those layers, there is a transfer of electrons and a counter transfer of ions. And when that happens, the opacity of that electrochromic coating changes. This, in a sense, is what changes the visible transmission and the solar heat gain of the IGU. So depending on how much voltage, how much current you're applying to the coating, you can actually control the solar heat gain and the light transmission. All right. So, and once the voltage is reversed, it can be cleared. Real quick, this is the performance values of the standard View Smart Glass product. There are 4 tint states, and starting from 0.40 SHGC all the way down to 0.09. And really, when it comes to thermal resilience under hot extreme conditions, this is the one that will really matter. And as you can see, I mean, this number is really, really very low compared to even the best performing low-E products in the market, right? And then finally, just one last slide on the product, electrochromic glazing, or in this particular case, View Smart Glass, has three components. One I already spoke about, that's the IGU, the dynamic glass. Then there is the network, which provides the power and the data to all of these windows. Every window has a separate IP address. And there are several other IoT applications that can be enabled by this existing already network, which is the first wire in the building. And then finally, there is the software algorithm, which controls the tinting of the glass. This is based on predictive models. We incorporate machine learning as well as some sensor inputs to kind of account for cloud cover, whatnot. So a combination of those things decides which of the 4 tint states an individual window should be in, depending on the time of the day and the intensity. All right. So with that, I just wanted to kind of give you an idea of what electrochromic glazing is, specifically View Smart Glass, and then we can move straight to the case study. So the first one, this is the measured case study, so to say the measurement study. This is a project in Boston. It's called Fenway Center, Tower 2. This is that building over here. And this is an interior shot of that building. As you can, the apartment rather. As you can see, there's a lot of glass, right? So I mean, to my point earlier, a lot of these buildings have a significant amount of glazing. So the idea was, and of course for good reason, as you can see, look at the views and look at the natural light. So obviously there's a demand for this type of design, right? The question is, how do you maintain thermal resilience and comfort and still have this level of design freedom? So the study design was set up to look at 2 identical units, about 1,000 square feet, for 5 days in summer. Now, this whole building has electrochromic glass installed. There is no regular low-E glass here. So to create a baseline, in one of the units, we had basically, we stopped the windows from automatically tinting. We locked the product in our tint state 2, which is 1 step darker than our lightest state, and that has a SHGC of 0.25. So we think that's a fair comparison to what a regular high performance low-E product would be. And then these units are air conditioned, but we had the HVAC turned off for the duration of the study to essentially simulate a loss of mechanical, which is kind of what I said was the objective of this study. So real quick, this is what this is the location of the apartment. So you can see these are 2 identical apartments, one on top of the other. This is a southwest corner unit, so it's going to get a lot of sun throughout the day. And this is the west facade, that's the south facade. They have, like I said, water loop heat pumps in each unit. And then the ventilation is provided by ERV in the hallways, and they have some operable windows. So that's what the building looks like. Now, this is the sensor that we use for measuring air temperature and humidity. This study was kind of more focused on using air temperature as the metric, so we didn't really make it any more complicated. This is just standard data loggers that were recording at 5-minute intervals. This is the location of the sensors in each of the 3 sort of distinct spaces. So there is one master bedroom, which is on the south side. And then there is the southwest living room, which has kind of windows on two orientations. And then there is one guest bedroom, which has a west window. So the sensors were 3.5 feet up away from the floor. And we carefully positioned them to be away from direct sun, because obviously we want to track the air temperature. We don't want this to get heated up by the sun. So this was essentially in the shade. Now, coming to sort of the thermal comfort assessment, right? So these are, again, if I'm sure you're familiar, these are the 6 factors of comfort traditionally that we are familiar with, that we use for any kind of thermal comfort modeling. In this case, we measured the humidity and the air temperature. The other things, obviously, the metabolic rate and the clothing was kind of an assumption based on the time of the year and assuming that people are working from home. This 1.1 met is basically somebody who's sitting and typing, kind of. Airspeed was essentially still air. We just assume that. And then the radiant temperature here, in this case, is assumed to be the same as the air temperature, only because we are looking at the comfort in the shaded portion of the apartment. So the argument here is, of course, if somebody is next to traditional low E glass, they're going to have experience a lot higher mean radiant temperature. And that's a fact. We know that. And that's one of the value propositions of dynamic glazing, in that it reduces that radiant heat. But if you are in an apartment where your HVAC is not working, there is really no good reason why anybody would be sitting next to direct sun, right? So that argument kind of doesn't work. So here the idea was that let's assume that people will move to the shaded area. So we don't have to explicitly look at the MRT near the windows, but the heat that's coming in through the window is eventually going to show up in the air temperature, right? Because the floors heats up, everything heats up, it eventually converts back. So I want to be very clear that I'm not at all suggesting that MRT is not important when you're looking at thermal comfort with windows. This is a slightly different scenario where we are assuming that people will at least move into the area. So we're not, that's why I made an exception. Now, once we have all of those 6 factors in, we can kind of compute the PMV values. Now, in this case, what I did is I looked at using the CBE tool, the great online comfort tool. I looked at what would be the appropriate threshold for air temperature, equivalent to like a plus 0.5 PMV, right? Which is sort of the discomfort threshold. And I agree, and I admit that this is probably an aggressive threshold, frankly, to assume that if you have no HVAC and you want to maintain like plus 0.5, it's probably going to be very aggressive. But there are a couple of reasons why I thought that this made sense. One is, first of all, this apartment is air conditioned. It's meant to be air conditioned. It's not meant to be conditioned naturally. Even though it has some operable windows, I'll show you later, those windows actually don't even open much. So right away, this, if you have to use a model, you have to use the PMV model. You can't really use the adaptive comfort model here. It's not going to work, because for an occupant who's used to, their comfort tolerances are going to be based on the air conditioned parameters, right? So one fine day, suddenly we can't just expand it to the adaptive comfort model. We have to kind of continue with, at least for this scenario. The second thing is, in a residential building, unlike in a commercial office, the challenge is if you are uncomfortable, you can't, it's not like you can go home, right? You're already home. So I kind of wanted to see like what, is there any portion of the apartment where we would be able to meet this threshold? And finally, it's likely that there will be inhabitants or occupants, maybe elderly or young, who might be susceptible to, might have health issues, right? So I intentionally kept this threshold a little bit aggressive to kind of check that out in this study. All right. So with that, we can kind of move into the data. So this is the measured weather condition for those 5 days in Boston. This is the outdoor air temperature. And as you can see, it was actually relatively mild, I would say, the first 3 days. And then it started getting into probably what I would call hot, and then maybe even very hot, right? Close to 95, right? And again, this is relative to Boston, of course. It's not Phoenix or Dallas. And here is the measured solar radiation on the windows, incident to the windows, right? So we had solar radiation sensors on the roof, so we were able to figure out what the radiation was. And as you can see, wherever you have a nice solid region, this is basically a nice clear sunny day, right? When you have kind of lower peak, or you have this kind of irregular shape, this is basically a cloudy, right? This, the radiation data is telling us that. And then not surprisingly, the west window peaks much higher, and then later in the afternoon, right? That's because of the way the sun's moving. And this being June, the sun is higher on the south facade. So you don't quite hit the same peak as the west facade. So all of this kind of makes sense. So from the weather conditions, it made really sense to focus on these last 2 days, where you had a decent amount of solar radiation and the temperatures were reasonably hot. All right. So let's look at the data. So let me walk you through this graph first. So this is the west-facing guest bedroom first. So this is the room with only the west-facing windows. So what you have here is our 3 temperature lines. The green dotted line is the outdoor air temperature, just to give us reference to what's going on. The dark blue line is the air temperature measured in the west bedroom with the view smart glass, and then the orange line is the same same room, temperature in the same room, but with the low E glass, right? So one thing we did is on the first day, we actually had the operable windows open for some time, and it actually did not make much of a difference. As you can see, it's actually getting warmer, even though the outdoor temperature seems to be falling down, right, at the same time. And this kind of goes back to my argument that, first of all, this specific apartment was not, there is not enough ventilation. There's just simply not enough flow rates to cool this apartment down, just based on what the amount of windows that are given. And that's not surprising, right? I mean, because they have air conditioned it, right? They're not really thinking of the windows actually providing conditioning. The windows are mostly probably for indoor air quality and maybe occasionally some comfort, but it's really not going to be sufficient for that. So what we did is, for the rest of the study, we actually closed the windows. We kept the windows closed, and because one, we didn't find that it was making much of a difference. The second argument was that when temperatures are going to get into 85, 90 degrees, opening the windows probably are not going to help anyway, right? At that time, if your indoor is cooler than the outside, then what value is in opening the windows, right? And this, of course, assuming that there is still ventilation through the ERV, through the hallway. So just to address that point, right? So this is clearly, you can see that the temperature in the low E window room is certainly going up, right? Whereas the view room, there is a delta throughout. And here is that comfort threshold of about 80 degrees, which is air temperature, which is equivalent to that plus 0.5. And if we were to now kind of zoom in, right, to these values, because I know it's a little bit harder to understand in graphs, so I just extracted out the temperatures above 80 degrees, right? So now if you look at it, you can see that there is a significant delta, right? Like 4 to 6 degrees delta between, on the hottest day, between the EC window, view smart glass, and the low E. And then put a little bit more context to this, if I were to overlay, since we are talking PMV, we can, then I kind of bring in the counterpart, which is PPD, percent people dissatisfied. If I overlay that, you'll notice that, to my earlier point, the plus 0.5 is a pretty aggressive comfort threshold to even achieve without any mechanical cooling. So if I were to kind of start from the 20% above, there is actually no discomfort when it comes to the view smart glass or EC room, but there is definitely discomfort with the standard product, right? I mean, the standard low E window, right? And that's pretty clear here. But again, I wanted to be true to what the data is, so I'm presenting it. We can interpret how we want, but I think it's reasonable to assume that, yes, this is not, there is maybe a little discomfort, but it's not as extreme as the other thing, right? So, and again, the other thing is, if you look at the hours, the extent of discomfort is also much more, right? It kind of starts around noon and kind of persists all the way till the almost midnight, right? So that's another factor. It's not just the temperature degrees, but it's also how long it persists. All right, so that was the west room. Now, if you look at the southwest living room, I think by now you're kind of familiar with the design of this chart, so I won't go through everything here, but I'm going to skip quickly to the delta here. So similar effect, maybe slightly less because this is southwest and it has a slightly bigger volume of air. I mean, volume, the room is slightly bigger, the living room. So it's not as extreme as the west, but still same issue. You have a delta here, and clearly even on this day, for example, on the 27th, there's really no discomfort at all with the EC glazing, right? But you have discomfort here, which gets much worse on the following day because the temperatures outside are now 95 plus, right? Okay, so same thing here. And then finally, we move to the south-facing master bedroom. Now, this one is actually the one that has the least direct solar exposure, right? Because this is a south window. This time of the summer, it's going to get relatively less direct sun. However, it's still not immune from the outdoor air effect, right? That's still there. The conduction through the glass is going to happen. That's still there. So there's some effect, but not as much. So I would, looking at this data, there's basically no discomfort with the EC, there's definitely some discomfort with the standard glass. And I think the takeaway here is that if you are designing for thermal resilience, there should be at least one area, if not all of it, but at least one area of your building or apartment or unit where you can probably seek refuge in, so to say, right? So in that case, in the EC scenario, even if we were to argue that, hey, even this is discomfort, even though I'm saying this is probably very mild, even if we had that argument, I would say that at least you could move to the south side of the apartment, right? And you would be reasonably better off. But even with the south side, with the low E glazing, you're still not completely out of that discomfort rate. And it's not surprising why that's happening, right? I mean, this is an apartment unit. Even if there is no direct sun necessarily on the window, the air is mixing right within the apartment. So obviously, if the west room is getting heated up, the southwest, it's eventually going to go up, right? So that's kind of the phenomena happening. So that's the takeaway from this study. I'll be happy to take questions after the session. I will continue on to my simulated study. Let me time check. Oh, okay, perfect. All right, so that was rather interesting study, and we can move on to the simulated one now. Okay, so this is a simulated study of a commercial office with curtain wall glass, which is again kind of the standard design, right? What everybody desires for. So we took a building like that, and here's my study design. Took a floor, sort of standard perimeter core zoning with dynamic glass or low E windows with shades. All right. Looked at 4 locations, picked like the hottest day from the TMY file, and then simulated a power failure from 2 p.m. to 8 p.m. in the energy model, right? And I'll explain what that means. The logic behind the 2 p.m., 8 p.m. is that this is typically like in a summer afternoon is when you would expect the cooling load to be sort of peak. And if anything, that's when either the grid will be stressed or maybe your equipment gets stressed or something or the other. So that was kind of the argument for taking the afternoon versus the morning. But I mean, technically it can happen any other time too. But that's the what I assume for this study. So here's a little bit more about the building model itself. So these are the dimensions. As you would expect, the shorter sides are facing east-west, as any reasonable architect would orient this kind of a building. Then the color code shows you the kinds of walls. So obviously the core area is the solid walls. I chose air walls for these zones intentionally so that I could use air mixing in the energy model, which is what kind of will happen in an open office environment anyway. So that's why these are air walls. There are fan coil units for taking care of the sensible loads. And then there is a DOAS with heat recovery for the ventilation. All right. So fairly standard system, nothing complicated or fancy here. And as you can see, it's all curtain wall glazing. So pretty much I would say 70% glass, maybe even more, right? Again, real quick, this is I've already talked about this. So this is the EC glazing, 14 states. This is the traditional glazing model that I selected, again, 0.27. So a reasonably good low E product and shades, because I know there will be shades, right? So I'm assuming that people will have access to some kind of fabric shades, 3% openness. So all very standard assumptions that you would expect. The only difference, of course, is that the shades will be kind of manually operated, whereas the dynamic glazing is automatically controlled, right? I want to address the power demand of the EC glazing, because I think there is definitely one aspect of this, like if power does go out, right? Clearly, if electrochromic glazing is a powered window system, how much power can it be put on a backup system, right? Or a backup power source. And to support that argument, I'm basically showing you that for this specific example, there are about 147 IG 5 by 10 feet. And the peak power needed to tint all of the IGUs at the same time, which is again unlikely, probably don't need to tint all the windows at the same time. Probably will be tinting more on the side that has the sun. But even if we did all of that, it's really only at 500 watts, 515 watts, right? And it's even less when you want to hold the tints. So I just want to show you that this is not something that this should be fairly easy to support with some kind of a backup battery or something, some power source. However, having said that, once an IGU is fully tinted, it can actually maintain tint for up to a day or more without any additional power. Yes, it will clear out eventually, but it will take probably a couple of days. So clearly, if you have lost power to everything in the building, then I mean, you have to fix that, right? You can't rely on just dynamic glazing to maintain comfort for days on end without power. So I just want to address that question because I thought that might come up. So clearly, the takeaway is very low power consumption. Once the IGU is tinted, it can stay tinted for a couple of days at least, depending on the size of the IGU. Or alternatively, if you really want to make this part of your resilience strategy, it's probably best to have some kind of backup power to then be able to actively control the tints. Now, let's get into the assumptions for the energy model itself. So I assume that, very standard lighting power, equipment power densities during the regular time, occupant density is 200 square feet. When the power goes out, I kind of assume that there would be reduction in the lighting, and there would be reduction in the equipment power as well. Kind of just my assumption that there will be still some power available, because if you're assuming people will still be there, can't be any light or power, then I mean, what are they going to do there, right? So assuming that there is still some limited lighting and power available, the occupant density stays the same. That's kind of the premise of it, right? If all the occupants stay back, what's going to happen, right? How does that look like in terms of the temperature? So that's the internal loads. Then when it comes to the HVAC operations, the fan coils obviously are designed to maintain the set point, but when the power goes out, the fan coils completely shut down, right? So I just use that availability schedule plus do that. And then, however, the DOAS will continue to provide minimum outdoor air. Again, this is assuming that there is some kind of either backup power, or assuming that the HVAC, maybe the chiller failed or something, right? The logic, again, is probably clear to you. If you are in an environment with, a lot of people, and if you have no outdoor air, no operable windows, then frankly, the indoor air quality might become a bigger problem than thermal comfort, right? So that at that point, I think it's kind of unrealistic to expect any thermal resilience if you have no way to ventilate the building at all. So there's still some minimum air coming in, but there is no conditioning happening. And then finally, the interzone mixing that's there in the default model condition. I reduced that because now the assumption is that the primary airflow from the fan coils is stopped, right? The outdoor air is going to be a much lower flow rate. So I accounted for that. I adjusted the energy model air mixing to kind of reduce for that. And with that, so that's kind of the model. Now we revisit our thermal comfort model again, very similar to what we saw earlier. This time, because it's all simulated, I kind of, and as you can see, this time we did simulate the radiant temperature also. It's not set equal to air temperature, anything like that. I went back to the more conventional SET metric for this analysis, right? And here I found that there is some literature on this. LEED actually has a pilot credit on passive survivability, which says that SET of less than 86 is kind of the ideal target. When I looked at this in relation to PMV, this is like plus 1.6. So this is definitely, this is discomfort, right? This is definitely in that range. It's not mild discomfort. And I think it kind of makes sense that for an office, it has to be a little bit higher given the internal load, given the density. I think it's going to be unrealistic to expect that if HVAC goes out, it's going to stay at 0.5 PM, like a residential, right? Just too much internal heat gain and other things going on. So this made sense for me to go with, and that's kind of what the literature is supporting as well. So about SET of 86 is kind of the threshold I use for 30 degrees. Okay, with that, let's look at the Let's look at the weather. This is, of course, from the TMY weather file for each of these 4 locations. So I picked a day which had high temperature and high radiation, right? That's the premise of this study. Just high temperature alone is not what I'm looking for. I'm looking for a combination of high radiation so that the glass, actually the solar heat gain comes into play, right? That's what we want to really understand between smart dynamic glazing and regular glazing. So again, New York kind of in the goes up to around 90, San Francisco and Seattle maybe a little bit milder. Actually, it does go up to close to 90. Dallas, not surprisingly, is the one that is kind of much hotter, right? 105 plus. And then all 4 are kind of have clear sky solar radiation. This is just an indication of whether it was a clear sky day or not, right? So this will come in handy when we look at the rest of the 3-4 slides I have left, when we look at the results. But I think it's good to kind of look at the temperatures once again, because this helps you understand clearly Dallas is going to have much higher air temperatures throughout the afternoon. It takes a while to even cool down. Seattle, San Francisco is probably the mildest. Seattle is maybe next, and then New York is maybe kind of a little bit between Dallas and Seattle, right? So now let's look at the results based on this. So here are the results for, we start with San Francisco. So let me kind of orient you to the graphs here. So there are 4 identical graphs representing each of the 4 perimeter zones. The metric is SET, standard effective temperature, right? And what you see here is, and the green line represents our threshold, which I just said, SET of 86 or 30 centigrade. And these 2 lines, one is the blue line is EC glazing, and the orange is the low E with the shades, right? And this box represents the time when the HVAC has been turned off, right? To simulate that absence of power or equipment failure, whatever that is, right? So from 2 to 8. So not surprisingly, there is a drift in the temperatures in all the zones, right? But it's worst in the west zone, right? I mean, that's not surprising, because the west is the one that's going to get all the solar radiation in the afternoon, right? However, because, like I said, this is an open office environment, right? So all the zones are getting affected, right? Once the HVAC turns off, the air is going to kind of start mixing, heating up. The effect is definitely more localized in the west perimeter because the system stops from 2 to 8. But you can see that in the other zones. But clearly there, it's not really getting into that discomfort threshold if we assume that 86 is our threshold, which I said earlier is fairly high. I mean, it's like 1.6 PMV. That's like 50% PPD or something. So here, the takeaway is that, there is an increase in SET with both glazing options. But as you can see in the low-E shade scenario, is definitely exceeding that discomfort threshold, right? And with the smart glass, you're kind of going up, but it doesn't really hit that. And if you remember, San Francisco, at least in this TMY weather file, the outdoor temperature is not that high. It's just about getting to 80. It's kind of 90. It's below 90 for the most part. So I wouldn't call this a heat wave, frankly, right? So even in that scenario, this shows you that you don't need the outdoor temperatures to be very high. If you have a lot of solar gain, it can actually lead to a big problem if you have a lot of glass and you can't control the solar gain. Even with internal shades is not going to make any difference, because once the shades are down, the heat is still in. And if there is no air conditioning, there is no air to cool the shades down or anything. I mean, that heat is still inside, right? It's going to heat up, right? So that's kind of what we're seeing here. Now, if we move to slightly warmer locations, we go to Seattle. So similar phenomena, right? All the zones are kind of going up. And this kind of shows you almost same magnitude, which makes sense. The air is kind of just mixing up. But the west zone, again, with EC, you're kind of just getting to that threshold, but not there, maybe slight, but definitely you're going to exceed that for the low-E glass and for longer hours, like I said. Both are important. What's the peak and what's the sort of area under the graph, so, right? So again, clearly the data suggests that there's going to be discomfort. Now, when you get into New York, here, similar scenario, but I think the temperature is now kind of a little bit above 90. So you have a little bit of effect even in the smart glass scenario, but still lower, I would argue, than the low E. And then finally, when you get to Dallas, which is where you have temperatures in excess of 100 degrees, this is where you see that even on the smart glass scenario on the west perimeter zone, you do kind of see that it's going up by maybe maximum couple of degrees, while it's more like 6 degrees on the low east side, right? So much worse, I would say, relatively speaking, than compared to. And even on the other zones, you see that they're kind of drifting up closer to that threshold, right? And this is purely because of the outdoor air temperature in Dallas, the 100+ degrees, right? So when you get to a point where the outdoor temperature is that high, I think you're kind of hitting the limits of what you can do in a standard curtain wall building, right? If you have no other passive feature, right? Which is what this building is, right? So I think kind of that's a takeaway. So with that, I think I'm almost done here, Gokul. I'm just going to probably one more slide. So I think this is interesting. This makes sense to me. This makes sense to me. And I want to be objective. This presentation is not about saying, hey, with dynamic glass, you don't need AC, right? That's kind of, that argument wouldn't make sense, right? If indeed you could maintain comfort 100+ degree days without any air conditioning, why would you even have it in the first place, right? So that's not the argument I'm making. The point here is that with a product like EC Glazing View Smart Glass, you have lower discomfort even under very extreme conditions, and you have lesser hours of discomfort, right? Which is the key thing. It allows you to, if it's a commercial establishment, allows you to continue your operations without too many disruptions. Or if it's residential, it allows you to potentially even avoid extreme health effects, right? So this makes sense to me. So with that, I kind of want to just conclude on my last slide, summarize all the points we went through. Clearly, the low E glazing scenario was not able to maintain comfort, as you can see, even when temperatures were not that hot, frankly speaking. Like less than 90 degrees outside is pretty standard in many cities now, and was still heating up, right? EC glazing worked pretty well for the most part, and except only when outdoor temperatures started exceeding 100 degrees and you had full sun on the facade. You know, you're kind of pushing the limits of the conduction of the glass itself at that point. It's the material glass itself, right? It's not for EC glass. It's not a shortcoming of EC, but it's really at that point the material glass, right? How much can you actually block in terms of U value? So I guess one way to look at it is that if you're in climates like that, it probably makes sense, goes without saying, that you have some kind of backup cooling, right? It might not be necessarily the full system, maybe some system that allows you to temper the air a little bit, maybe not, it doesn't get it down to like 75 or whatever, but maybe even 2-3 degrees cooler might make the difference. So I don't know exactly what that system would be, but that's kind of something to think about. I won't talk about the fact that EC glazing, like I said, is a low voltage, low power window. So which you can easily put on backup if your concern is, hey, I want to have full control over the facade in the event something like this happens. However, if, like I said, for the most part, the likelihood is that power failures or even potentially extremes, conditions will be in the afternoon, more so than in the morning when we're talking overheating. And in the afternoon, dynamic glass will already be tinted, right, on the facade that it matters. So even if the power goes out, it's going to stay tinted for at least a couple of days. So you have some that's kind of your backup, right, in terms of fixing whatever is going on with the rest of the building. And I think one point about residential spaces is that it seems like you would think that it's more critical than compared to commercial, because this is where occupants really can't really go anywhere else often. That might be your only space to be. And there could be occupants who are vulnerable to heat stress. So, assisted living, long-term living, or even, it could be any regular apartment, and there might be people who are susceptible to that. So I think that's kind of where the thresholds for resilience might be a little bit tighter and compared to commercial office. And then in an office, in commercial buildings, I think given the internal heat gain and the fact that you kind of maintain CO2 levels or indoor air quality kind of levels, it does make it, I think, in my mind, more challenging to kind of maintain comfort if you have no mechanical cooling or ventilation. So at a minimum, I think there has to be some way to provide ventilation and, like I said, possibly some form of backup cooling especially for conditions where your outdoor air is exceeding 100. All right. So with that, I think Gokul, I'm done, and this is my email. I'm more than happy to continue this discussion. I know there's a lot of research, there's a lot of points around this topic. It's a very interesting topic. I'm very willing to kind of hear your thoughts. We have 10 minutes left, so maybe we won't have time to cover everything. But please email me with anything. Go ahead, Gokul. I can't hear you.
Can you hear me now?
Yeah.
Okay, thanks. Great presentation. It's great to see electrochromic glazing being talked about and modeled. It's not something, as an energy modeler, I wasn't modeling this day in and day out. So dynamic glazing, it's a very important topic, and thanks for presenting today.
Sure.
We do have a couple of questions from our viewers, and I have some of my own too, but I did want to point out that this video would be available on our YouTube channel. Please like the video and subscribe to our YouTube channel if you enjoy our webinars. We also encourage you to consider joining the IBPSA-USA Research Committee, which is hosting this webinar. I have pasted the link to the Google Forms for you to join, or you can email us at research@ibpsa.us. I do want to also say that we are having a pause in the month of July. We will be back with this series in August when Won Hee presents about daylighting in buildings. I did want to, cool. And I have questions, but I think maybe I'll open it up to our audience. So first is Libu Babu. He says, is there a study showcasing impact on peak loads in this space?
Yes, there is, Libu. If you could email me, I could probably provide you some information. But and you're absolutely right. I think one consequence of thermal resilience or thermal comfort is that there will be reduction in peak load. I think that's a natural sort of factor, right? So you're absolutely right. If you email me, I'll share a couple of studies with you.
And Libu, you're also I gave you permission to talk. So if you want to have a follow-up, please do so.
Oh yeah, no, that's the only question. Thank you. I will reach out to you personally.
Sure, Libu.
Awesome. Thank you. Jyotis Anand is our next question. He says, thanks for the great presentation. I'm wondering whether you have estimated payback periods for electrochromic view glasses for air-conditioned buildings in hot regions, specifically places like Phoenix, Arizona.
Yeah, good question, Jyotis. Frankly, it's a bit hard. It's a harder question since there are a lot of factors to consider when you're doing a payback analysis for a product like this, unlike a conventional glazing product, because this is, like I said, this is really more of a system than just a glazing product, right? There are a lot of other benefits. Speaking of Phoenix, I don't know if you've noticed, the Phoenix airport, the new terminal is all viewed smart glass. There's some really cool, pictures and videos of what that is. And, Phoenix decision to choose that product was based on sustainability and comfort. So, they obviously were convinced of the payback. I can't quite give a specific number because, like I said, it really depends on the project, how much glass they're buying, right? And what the kind of the commercial deal is. But if you want to reach out to me, we can have a chat. If you have a specific project in mind, that would be even better. Then I can give you more specifics around that.
All right. Thanks, Jyotis. If you want to comment more, I have given you permission to talk, so go ahead. If not,
no, I was just wondering because nowadays people are more work from home, so I think energy load is quite doubled for most of the people in Phoenix. So I was wondering, is there any advantage of replacing the glass? Whether that will help them reducing the electricity charge, if they are working from home, things like that.
Oh yes, absolutely, Jyotis. And you're absolutely right. There is so multifamily sector is actually a very it's kind of, I would say, a booming sector for View right now. There's a lot of demand, exactly for the reason you said, that people are working from home and they kind of still obviously want to have access to views, natural light. They want a comfortable, healthy environment. So there is definitely a demand for it. Energy is one part for sure. Again, as you can imagine, if you are purely looking at the solar heat gain of the product, if you're going down to 0.09 compared to a 0.25, I mean, you can imagine that there will definitely be like energy saving. But I want to say that we kind of, it's really not just about energy only. It has to be also about comfort and the experience. So I just want to temper with that. Like, if we look at this as purely energy savings product and try to do payback, this is not really, that's not how model works. So we really don't look at it that way. But absolutely, it's a sustainability. We enable that. Net zero energy goals, all of these are critical, and you can help with that. But it's also primarily a comfort and experience product.
thanks. Yeah, that's a good clarification to make. Thanks, Ronnie. I do have a fellow glazing modeling enthusiast, Matt Dahlhausen, next. He says, did you show the impact on daylight autonomy with electrochromic glazing, both the quantity and quality of daylighting? He also asks, how does electrochromic glazing change the wavelength distribution of daylight and color rendering?
Okay, great questions. I think the second one, I might actually be out of my, sort of might be a little bit out of my domain, Matt. And I think we have communicated before, I'm pretty sure, Matthew. If you don't mind sending me an email, I will give you the specific response to the wavelength questions. We have all that data. Regarding the SGA, this was more a thermal resilience study. So I really didn't look at that aspect. But we do a lot of this type of modeling, Matt. We have, actually, we have a daylighting team. We have a director of daylighting who is an expert in radiance. So we know all the modeling workarounds or methods of how to model dynamic glass. I'm sure I'll be able to, he'll be able to address all your questions. So if you don't mind just sending me an email, I'll kind of, with your question, I'll make sure you get all the answers.
Matt, I also gave you permission to talk if you wanted to follow up.
Sure. Yeah. Can you hear me now?
Yep.
Yes. Go ahead.
Yeah, thanks. Yeah, I think we worked a little bit a while ago when I was at Integral Group doing consulting work, and I was modeling some view glass for some projects.
Yes.
Yeah, I don't think we actually ever recommended electrochromic glazing on projects, largely at the request of our daylighting designers because of what it does to the daylighting quality in the space.
Right.
I'm not sure how much that has changed, and maybe you can send me information on that. But I guess one comment I wanted to make was that I think that the appropriate counterfactual for controlling solar gain is not just a fixed solar heat gain coefficient on the glazing plus shading. It's also looking at fixed exterior shading devices or even automated exterior shading devices, which was sort of like our best of the best in terms of both loads and daylighting and all these other factors. It's also a building that has just lower glazing ratio, and that's becoming harder with code to do that. So I'm curious, when you're presenting this to clients, are you showing all those appropriate counterfactuals, or are you just sort of sticking to that the architect wants 90% glazing ratios and they're not going to budge from that, and that's how you're keeping your product viable?
Yes, let me address your first question. So I want to say that probably what you've seen in terms of the color quality is our previous generation of product. It has certainly changed. So our new generation of product has a very neutral tint. It's actually the most neutral in the EC industry. I'll be happy to send you the specs. I think it's going to definitely change your mind, because we have had, this was a concern, Matthew, not just from Integral, but from several other designers and engineers. And I want to say we have successfully addressed that, I think. So I'll give you, once you email me, I'll give you that. When it comes to the facade, I agree with you that an external shade can also probably work. This was, to your point, showing a more typical construction, right? Most of these buildings don't have external shades or automated external shades. So I was kind of looking at a scenario where you're taking a typical design and you only have the glazing to work with. However, for the shade, yes, they probably will be effective. The only question is, can they maintain outdoor views, right? You probably can't. If you're talking about a west facade and you have automated blinds coming down, you're going to have to basically close it up entirely, right? There's really no other way you're going to be able to stop direct sun on the facade. So our argument would be that you might be able to get a similar solar heat gain, but then, I mean, you're losing views, right? And the name of our company is View for a reason. Is because the product always maintains. So yes, absolutely. I think there are pros and cons. I'm not saying there is a one size fits all design for all projects, right? You're absolutely correct that there are other solutions out there, but this seems to be kind of the more streamlined approach, kind of my opinion. But when the project does have that kind of external shading, we definitely factor that in the analysis. We then consider what's kind of compare that as the baseline. But this was meant to show a more typical facade design, which is what we encounter for, I would say, like 80% of our projects.
Okay, excellent. Thanks for clarifying. Yeah, I'm interested in seeing the new tint data.
Yeah, I will give you the full, you can geek out on all the data. I'll give you all the spectral data, everything.
I want to be CC'd on that email too. I want to
Yeah,
not necessarily geek out, but I'll be interested.
Sure. Okay.
We are 2 minutes over time and I have to run to another meeting. So I'm gonna close. I don't see any more questions here. So I'm gonna close the discussion. For our YouTube members, this video would be available as soon as I finish my next meeting. So in an hour in our YouTube channel, please consider liking and subscribing the channel. Thank you, Ronnie, once again for accepting to do this presentation. Really great to have you here. And thanks to our attendees as well for HBUS's great presentation. Yeah, thank you. And thanks to our attendees as well for being able to attend this presentation and take away some relevant information. We hope you all have a happy Thursday. Bye, everyone.
Thank you. Bye.